Hello everyone, welcome to the course on computer-aided drug design. Today we will talk about 3D QSAR. We talked about the normal QSAR. Today we will talk about 3D QSAR, which means the conformations, the molecule stake becomes very important, and then we try to superimpose those conformations and then try to get some activity related structural features. Okay, so here conformations become very important, the molecule that occupies, because as you know, when the molecule goes and binds into an active site of an enzyme, the conformation plays a very important role. Okay, so before that, if you remember in the past few lectures, we talked about QSAR and other so we used a lot of these databases. Then we used Dragon, Swiss ADME, KIMDES, OChem to get the various descriptors. Okay, then I also talked about build QSAR, which almost looks like an Excel, and then I showed how to build that. Then if you are interested in the semi-empirical quantum mechanic descriptors like electron energy or proton and highest occupied molecular orbital energy or lowest unoccupied molecular orbital energy and so on, you have to use MOPAC. JMOL is for visualization. Okay, so we looked at all these. Now there are more softwares on QSAR using this link. For example, I'll just show you. We will not have time to spend on so many. Okay. So okay, so a lot of softwares you can see on QSAR. You can start exploring, as you can see in this. Okay, a lot of softwares there, QSAR, and some of them are downloadable and some of them are based through the web server. So we will not, as I said, have time, so please start exploring. Okay, so what is this 3D QSAR? The quantitative relationship between the biological activity of set of compounds and their three-dimensional properties. Okay, so ultimately, like I said, the molecule occupies a certain conformation which is very important for the activity. So not all conformations may be useful for the activity, because as you know, it finally goes and binds to an enzyme, so the conformation plays a very important role. Okay, so there are different approaches. One is called the molecular shape analysis approach. So what we do here is you look at a common overlap steric volume and potential energy, because it's a molecular shape between pairs of superimposed molecules. They are correlated to the activity. So it uses common volumes, provides some insight regarding the receptor binding site shape and size, because it's more to do with the volume. That's the molecular shape analysis. Second is called the molecular topological differences. Okay, this is the another approach. So what it looks at, the minimal steric topological difference approach. Minimal topological difference use a hypermolecule concept for molecular alignment. Then it correlates vertices in the hypermolecule to activity. Okay, that's cool. That's molecular topology difference. The third approach is called the comparative molecular movement approach. So basically it looks at the movement descriptors of the molecular mass and charge up to and inclusive of second order. This is called the comparative molecular movement approach. The fourth approach is called the self-organizing molecular field analysis, SOMFA. So it divides the molecule into actives, inactives, then a grid probe process that penetrates the overlying molecule. So you overlay all the molecules, and then you look then you have a probe molecule, and then the resulting steric and electrostatic potentials are mapped on the grid points, and they are correlated with the activity using a linear regression. Okay, that's the fourth approach. The fifth approach is called it's also a grid based technique. Okay, it is called the comparative molecular field analysis, COMFA. This is very common. If you look at 3D QSAR, most of the software, commercial softwares use this. So this is also a grid based technique. This was introduced in 1988 on the assumption that the drug receptor interactions are non-covalent. As you know, the drug goes and binds to an active site. It doesn't form a covalent bond, but mostly non-bonded interactions like electrostatic, van der Waals, hydrogen bond, and so on. So the changes in biological activities or binding affinities of sample compound correlate with the changes in the steric and electrostatic fields only. Steric and electrostatic fields. So these field values are correlated with the biological activity using partial least square analysis. This is a statistical tool, a statistical approach. So we will not go into that. But what the approach is, they have a probe. They first will superimpose all the molecules, and then they have a probe, and then it looks the probe moves at different locations on the grid, and then it determines the steric and electrostatic fields interaction, and then that is then correlated with the activity using a partial least square technique. So this is the reference which I would like to acknowledge for all these 5 techniques which they describe more in detail. You can have a look at it if you are interested to understand more of that. So the commercial softwares also use Tripos, MSI. They all use these type of COMFA analysis, volume surface. They all use for 3D QSAR. Okay, so the molecular field may be represented by a 3D grid. Okay, so you divide, you create like a big rectangular box, and then divide into small grids. Each voxel represents attractive and repulsive forces between the probe molecule and the target molecule. So if you have the target molecule placed and you have a probe molecule placed at each of this grid, you look at the attractive and repulsive forces based on steric interaction, electrostatic interaction. Okay, so you calculate that. So it can be a water, octanol, it can be even carbon, simple oxygen, hydrogen, H, not hydrogen, H. So each grid voxel corresponds to 2 variables in QSR, steric and electrostatic. Then the partial least square technique is applied to compute the coefficients. Okay, once you place a probe and then measure the steric and electrostatic interaction between the molecule and that probe. Okay, you measure that, and then you try to correlate with the activity. Okay. These properties are known as fields. Steric field, it's an indication of the size and shape of the molecule. Electrostatic field, electron rich poor regions of the molecule. Okay, then hydrophobic properties are relatively unimportant. It doesn't bring in hydrophobic property. The COMFA 3D looks at only steric and electrostatic, so it doesn't bring in the hydrophobic interaction at all. A grid with energy fields is calculated by placing a probe atom at each volume. Then you calculate the steric using Lennard-Jones potential. You calculate the electrostatic Coulombic interactions. Okay, so the probe could be sp3 carbon atom with charge +1. That's the probe. Okay, so what are the advantages of this? No reliance on experimental values. We don't need much of experimental accuracies. Can be applied to molecules with unusual substituents. Okay, it may be very difficult to do with 2D QSAR. It's not restricted to molecules of the same structural class, because when we talk about in the normal QSAR, it's always good to use same class. So your QSAR, if you are developing for ethers, if you extend it to aldehydes, sometimes it might not work. Okay, it's got predictive capability also. So what are the problems? The molecules must be optimally aligned. That's very important, because you have placed one on top of another. They are very different. Placing them may not be really practical. The molecules, flexibility of the molecules, because the molecules can take different conformations. If you have many rotatable bonds, that's a problem. Okay, let's look at what it is. So imagine you have a simple molecule like this. Okay, it's got okay, this is the, then this could be the conformation of the molecule. You identify the pharmacophores of this molecule. Okay, Pharmacophores could be, say, hydrogen bond acceptor, because these are all oxygens, or it could be a hydrophobic, okay, centroid. These could be the pharmacophore. So what do we do? Build each molecule, identify the active conformation for each molecule, identify the pharmacophore. So if you superimpose all of them, then it's easy. So these knowledge was taken from this reference. You guys can have more look at this to get so I like to acknowledge that. Then you place the pharmacophore into a lattice of grid points. So we may have a rectangular box and you be divided into lots of grids, so you place it. So this could be a rectangular box, and then you divide it into small grids, and then you place your molecule inside. Okay, so these are the grid points. Each grid point defines a point in space. Okay, place the pharmacophore into the lattice of this grid point. Okay, position molecule to match the pharmacophore. Okay, like this you have matched, so that these pharmacophores are matched exactly on some grid points. Each grid point now defines a point in space. Now you can have a probe atom, like I mentioned, it could be sp3 carbon. So what we do is we move this sp3 carbon at each of these grid points and measure the steric interaction with this molecule or repulsion, electrostatic interaction or repulsion, calculate. So we'll get lots of data at each of this grid point. So suppose you have 1000 grid points, you will get 1000 steric interaction data, and then 1000 electrostatic interaction data. Okay, so you will have, and then you try to correlate that with the activity using partial least square method. Okay, so probe atom, like I said, it could be a sp3 carbocation, it could be even H, or it could be O, and so on actually. So you place each of these molecule at the grid point. Okay, once we do that, then so obviously when closer the probe atom to the molecule, higher is the steric energy. So it defines the shape of the molecule by identifying grid points of equal steric energy. So you can get a contour line on this. Okay, you can have favorable electrostatic interactions. That means with positively charged probe indicate molecular regions which are negative in nature, or unfavorable electrostatic interaction. That means positively charged probe indicate molecules which are positive in nature. Okay, so it could be favorable or unfavorable. Then we can have electrostatic fields by identifying grid points of equal energy. Those are all called a contour line. So we keep repeating the procedure for each molecule. So you place each molecule and then you repeat the same procedure. So for each molecule you'll get lots of data with respect to each grid point related to the electrostatic interaction or repulsion, steric interaction or repulsion. Then compare the fields of each molecule with their biological activity. So obviously we can do a QSAR, which is called the 3D QSAR. So you identify steric and electrostatic fields which are favorable or unfavorable for activity. So so compound 1, 2, 5, 3, 4, 5. So this is the biological activity. So this could be the grid points. Okay, so at each of the grid points you have the probe, and then you get the steric interaction. Then when you place it here, you get some number. When you place it here, you will get some number. You place it here, you get some number, and so on with respect to steric. Again with electrostatic, when you place it here, say 001, you get some number, and so on. So then you take the second molecule, then you take the third molecule, then you take the fourth molecule, then you take the fifth molecule. So when you keep doing that, you get lots of data with respect to molecular weight, and you want to correlate with the activity, and you will get lots of each one sort of could be a descriptor. Of course, like normal QSAR, we cannot just take one and then try to get a regression relation, but we make use of all of them. That is how partial least square technique works. You take all of them and create some composite descriptors and then try to correlate with the biological activity. Okay, that's how it does. Okay, So you use a partial. So QSAR equation will be activity like this, like this, like this, like this, like this. Okay. So I will not go into the statistical technique called partial least squares analysis. So you people have to look into some standard book. So let's also look at a software. This is a freely available software. It's called 3dqsar.com. So all you need to do is you need to get a username password. So with that username password you can log in into that. Okay, you can log into that. Okay, so this is the QSAR. Yeah, this is the internal menu. So you need to get in username password. So you write to them, they'll give you access. So I had already loaded some molecules. These are anti-inflammatory. Okay, so I've loaded 4 molecules. I've loaded their activities also. These are selective COX-2 inhibitors, as you can see. Okay, this is Bextra, this is DUP, this is Rofecoxib, and this is called Celecoxib. Okay, so 4 molecules I have loaded, and I have also loaded their activity values also here, as you can see here. Okay, these are the activity values. As you know, DUP has the highest activity. So these 4 molecules are selective COX-2 inhibitors. You can load it through SDF file. I can load more molecules, add another molecule, or even draw molecules. Okay, so these are all anti-inflammatory drugs. Okay, so I have this. I can go to the models. I can say build a model for selected data set. So the probe atom could be C3, that's the carbon, sp3 carbon. Like I said, it can be O3 or H or C2 or N3. Okay, so I can say O, for example. Probe charge, I could change it to -1 also, both steric and electrostatic. Okay, build 3D QSAR now. Running. So I had done before a couple of them. Okay, now I'm this is oxygen. I have a C3 here, so we can have a look at this if you want. It gives you the Q square. It gives Q square. It's not very good. Okay, doesn't matter. View selected model results. Okay, so it gives you some idea about the model results. As you can see, this is the R square, Q square for this. This is R square is good, Q square is not good for this model. So we can view experimental recalculated. So it gives you experimental value fitting, and then it gives you the cross-validated R square. Okay, here and so on. We can also look at alignment. If you look at the alignment of these molecules, okay, go alignment. View aligned molecule. Go to conformations. Okay, view selected conformations. So these are the 4 molecules: Celebrex, Bextra, DUP, or Folk. So as you can see, this is the Celebrex, various conformations aligned. Yeah, this is Celebrex, various conformations aligned. This is Celebrex alone, single molecule which I had given. Okay, Celebrex is a single molecule which I had given here. Okay, this is Celebrex. As you know, this sulfur, double bond O, double bond O. This is various conformations of Celebrex superimposed on each other, as you can see here. This is Rofecoxib. This is Rofecoxib. Again, this got a sulfur and double bond O here. These are the various conformations of Rofecoxib aligned, so as you can see. So from this we can get the pharmacophore importance. Okay, this is the other molecule dupe. Okay, this also has got a sulfur O2 and these various conformations of tube, as you can see here. Okay, so this one has been completed just now. Yeah, this one has been completed just now. Completed, missing. You selected model results. Okay, so this is the different partial least square methods have been used. So you can see this R square is pretty good. R square, Q square is not good. Then these are different statistics. Okay, these are different statistics which has been used. Okay, so as you can see here, how the for each one of these models, how the R square varies. Okay. So this is the fitting here. Okay, this is recalculated predicted activity versus fitting here. This is cross-validated results, as you can see here. This is for Bextra, this is for Rofecoxib, and this is for Bextra, and this is for dupe, and this is for Rofecoxib. Okay. So this is steric, so we can look at steric and electrostatic here. Okay, so this gives you steric and electrostatic. So this is the fitting, this is the cross-validated, this is the fitting. Okay, this is a predicted versus okay, as you can see here, this fit is good for Bextra, fit is not good for Rofecoxib, fit is reasonably good for the dupe. Okay. So as you can see, go to models. Okay, as you can see, I have done anti-inflammatory, mostly COX-2 inhibitors like Bextra, Rofecoxib, DUP6. Okay, and then I used to probe C3, that is sp3 carbon, oxygen 3. Then I also used hydrogen, not hydrogen, H. Okay, I got different values. Okay, for both electrostatic and steric. So you can play around with that. Okay, so I can add more molecules. Here in this example I have just taken 4, so we can add more than 4. We can also have training set and test set also, as you can see here. Training set, test set we can do. Okay, so we can use draw molecules using bimole edit, or we can add multiple molecules, add single molecule, we can add okay, we can give the activity, and then we can give title for that, choose file. So we can choose the file, from where we want to. So it's quite user friendly. Okay, you can see done, then it can be a training set molecule, or it can be test set molecule. So it's quite simple. I suggest that you keep playing around with this particular software, because it's free, and you just have to get a username, password, and once you go to that, you can start playing with this. So the 3D QSAR principle is it superimposes the molecules. So each first you look at the molecules, you get different conformations, find out the pharmacophore, and then you place the molecule in a grid box so that the pharmacophores are properly kept, and then you take a probe. Okay, you take a probe molecule like atom, sp3 carbon, or it could be O, or it could be H, and then you place it at each grid point and calculate the steric and the electrostatic information. So how do you calculate the steric and electrostatic information? Use steric okay, steric you use the Lennard-Jones interaction. Electrostatic, you look at the Coulombic interaction, right? And then you place it at each grid point. When you do that, you get some numbers. Once you get these numbers, what do? You make a table, as I had mentioned. Yeah, make a table. So at each grid point, you, for a steric Lennard-Jones, you will get some number, and then electrostatic, okay, some electrostatic numbers, Coulombic. Then you keep the second molecule, aligned it properly, and then you do the same thing here, then third molecule, fourth molecule, fifth molecule. You also have the activity here. Okay, so you use, then you have too many descriptors, right? You want to make use of all the descriptors, unlike in your normal QSAR where we used to develop a model, a linear regression with one descriptor. Here we want to make use of all the descriptors, and that is why we use something called partial least square method. Okay, so it creates some composite knowledge based on all the descriptors. Basically these are all descriptors, like, okay, and then try to develop an equation for biological activity. Okay, so that is how it does generates the QSAR. And once you generate the QSAR, we can calculate R square, we can calculate Q square, so many things. So we can also have a just like normal QSAR, we can also have a training set, like I showed you in my example of software. Then you can have a test set, and then you can try to predict the activity of those test set compounds with the model which has been 3D QSAR model which has been generated using the PLS technique. Okay, so 3D QSAR is very powerful because ultimately molecules take a conformation and they go and bind to the active site of the enzyme. So that's a very, very important parameter. So some of the information which I've shown in the slides, taken from this reference as well as from okay, from this reference. Okay, so I like to acknowledge both. So there are many softwares for QSAR which I just briefly showed, and I also showed you some examples of softwares which can be run for both 2D QSAR as well as for 3D QSAR. So I expect that you can start exploring these. Okay, we will continue on a new topic in the next class. Thank you very much for your time.